Hello, good morning, everyone. Welcome to the next lecture of electronic devices. We are covering chapter number 2, and this is our lecture number 5. In the last lecture, we started with applications of the inverting configuration of the op-amps. In the last lecture, we talked about the weighted summer. We are going to continue with the applications. And so today we are going to discuss the next application that we can do with the inverting configuration, and that is an inverting integrator. Okay, so this is our third one, inverting integrator. So what we are interested in is in finding a time integral of the input signal. So how we can find a time integral of the input signal using an inverting configuration, this is what we are going to see today. Okay, so let me make the circuit diagram, and then we are going to solve the circuit. Right, so this is the inverting configuration that you guys have seen before so many times by now. And this is V naught of t. Vi of t is the input, and we want to find the time integral of this input signal. We have a resistor R. The current I R of t will flow through the resistor, and then the current IC of t will flow through the capacitor. Our capacitor is here, and this is the voltage that will appear across it. Okay, and we are going to consider this as an ideal amplifier with an infinite open loop gain. So we're going to have a virtual ground at this point, 0 volts. All right. So let's solve the circuit, right? So the first thing is we are going to have this IR of t. So if I will apply the Kirchhoff's law here, so I R of t is going to be equal to Vi of t over resistance. Right, so this current flows through capacitor and will accumulate charge Q on capacitor, right? So this current IR of t is going to flow through the capacitor and is going to accumulate the charge. So second thing that we can realize is if our circuit begins operation at time t equals to 0, then initial voltage on capacitor will appear at time t equals to 0, and it will be Vc. Right? So IR of t is the current that is flowing through the resistor. So this current, since we are going to have a virtual ground, so IR of t is going to be equal to IC of t. So this current is going to flow through the capacitor, and it is going to accumulate the charge Q on the capacitor. So if we consider the circuit begins its operation at time equals to 0, so it is going to so the voltage that will appear across the capacitor will be Vc as an initial voltage that is going to appear at the capacitor. So the total voltage, so let's write the total voltage Vc of t on the capacitor will be equals to Vc, its initial voltage, plus 1 over C, 0 times t, IC of t into dt. So in your earlier courses, you have in detail you have analyzed such RC and LR circuits and these time domain networks. All right, so this is the voltage across the capacitor that will appear. Now since our IC of t equals IR of t due to virtual ground, since we are going to have a virtual ground over here, right? So the current that is going to flow through the resistor is going to be the same that is going to flow through the capacitor. So that is why IR of t equals IC of t. Now let's apply the Kirchhoff's law at the at the output on the feedback loop. So it will be 0 equals IC of t into ZC. So this will be the impedance of the capacitor plus V naught of t. We can easily write this thing IC of t into ZC as VC of t plus V naught of t. So we can see that our output voltage V naught of t equals minus VC of t. Sorry. And we already know the value of the VC of t, so we are going to write down this value. So our V naught of t now equals to minus VC minus 1 over C 0 to t IC of t into dt. Now since my IC of t equals IR of t, and I know that IR of t equals the input voltage to the resistance, so I can replace this value over here. So V naught of t equals minus VC minus 1 over, I'm going to take the resistance out, R value out, 0 to t VI of t into dt. Now looking at the equation, you can see that this is integrating the time-based integration of the input signal VI of t. Right. So this circuit provides a time integral of input signal VI of t with VC as initial condition voltage and RC as time constant. This is also called as inverting integrator or Miller integrator, named after the scientist. All right. All right, so this is what we have discussed by far, that we can use this inverting configuration and we can find out the time integral of the input signal VI of t over here. So we developed the circuit in which, rather than using a resistor in the feedback, we connected the capacitor in the feedback. And we find out that our output voltage here will be equals to minus VC. Again, this is the initial condition voltage that is appearing across the capacitor at time t equals to 0. And then we're going to have VI of t is the input voltage, so it is taking the time integral of the input voltage. Now I am going to also analyze this thing in the frequency domain, and we're gonna make the Bode plots or the magnitude response plots of that as well. All right. Excuse me. All right. So frequency domain analysis. Okay, so before solving it for the frequency domain, I'm going to make it slightly more simple. And what I'm going to do is V naught, VI. So again, VI is the input. This is our Z1. Z1 is our impedance, which we know that in this Miller integrator, Z1 is the resistor. And then we have Z2, sorry. Then our Z2 in the feedback, we know that Z2 is a capacitor. In the Miller circuit configuration. Okay, so let's do the frequency analysis of this Miller integrator circuit now. So so if you guys remember, this is how we can write down the transfer function. Transfer function should be V naught of S over Vi of S, and V naught of S over Vi of S will be equals to, right, it will be simple, minus Z2 of S over Z1 of S in an inverting configuration. Right, since Z1 is a resistor, right, so it will be R, and Z2 is a capacitor, it will be 1 over SC. So if I will replace this, so I'm gonna get V naught of S over Vi of S equals to minus 1 over SCR. Now we know that S is equals to J of omega, so I can also write it as V naught J omega over Vi J omega equals minus 1 over J omega CR. So this is a transfer function of in the S domain, and in the omega domain of this Miller integrator circuit. Okay, so using this equation, now this is a simple complex number. You can easily find out the magnitude and the phase response of this transfer function. So the magnitude response will be equal to V naught of J of omega over Vi of J of omega equals 1 over omega CR, and phase response phi will be equals to plus 90 degree, right? You can easily find the magnitude in the phase of this complex number. All right, so after so this is going to be the magnitude response of this transfer function, and this is the phase of this transfer function, or of this specifically of this integrator. Now I am going to plot the magnitude response, or the Bode plot. Let me actually do that on the other one. So Bode plot of the magnitude response. Bode plot of magnitude response. Okay, so magnitude response was V naught J of omega Vi J of omega was equals to 1 over omega CR. Is that it? Yeah. Okay. So if you will plot this, again, if you remember that we usually make the Bode plot on the log scale. On the x-axis we have omega, and the y-axis we have usually in decibels, and V naught over Vi. All right. So what will happen at omega equals to 0, when our omega is going to be 0, our magnitude response will becomes infinite, right? So our magnitude response will becomes infinitely large, and we are going to talk about this just in a little bit more again. And then over here, when omega will be, so at omega equals to 0, right, our magnitude response will be infinite. Okay, and when omega it will be equals to 1 over CR, then if I put omega equals to 1 over CR over here, V naught over Vi becomes equals to 1, right? And 20 log of 1 will become 0. So that is why your magnitude response in decibels will become 0 at omega equals 1 over CR. And the decrease in the slope over here is, and this is similar to what we saw earlier as well, minus 6 dB per octave, or minus 20 decibels per decade, which means that there is a 20 decibel decrease in the magnitude as our frequency will double. So as omega will double, our magnitude will reduce to 20 decibels. All right, so our so at this frequency, when our omega naught over omega I was equals to 1, which was at omega equals to 1 over CR, so this frequency at which omega equals to CR is also known as omega int. It's called as an integrator frequency. Integrator frequency. Or inverse of integrator time constant. Okay. Now we are going to see another important concept over here. All right, so let me give you a quick backup summary before talking about that concept. So we started with the inverting integrator. We had this configuration, inverting configuration of an op-amp, and if sorry, we have a resistor with the input and we have a capacitor in the feedback, and we saw that this configuration is going to when we solve the circuit, we saw that this configuration will allow us to take the integration, time-based integration of the input signal. Then we did the frequency domain analysis and we built a transfer function of this Miller integrator, and we saw that, and we found the magnitude response and the phase response of this transfer function. The magnitude response came out to be 1 over omega CR. When we plot that magnitude response, this is what we get. We saw two important things here. One is when omega equals 1 over CR, and when omega equals to 0. When omega equals to 1 over CR, this is known as the integrator frequency, or inverse of the integrator time constant. And when omega equals to 0, we saw that, right? So if you're going to put omega equals to 0 over here, we can see that V naught over Vi magnitude response will becomes infinitely large. So this is what we are going to discuss more now. So important notes: at DC, omega equals to 0, capacitor behaves as an open circuit, and there is no feedback. So magnitude response becomes infinitely large, like open loop configuration. Right, so this is a concept that we discussed. When omega will become equals to 0, right, our magnitude response becomes infinitely large. We can also see this phenomenon just by looking at the circuit over here, this circuit, right? We have a capacitor, and when this capacitor at omega equals to 0, we know that XC, right, 1 over J omega C. So when omega becomes equals to 0, our XC becomes infinite, so it behaves like an open circuit. So at omega, at DC's at DC frequencies, or at omega equals to 0, our feedback will be lost, and we're not going to have any feedback. And we don't have any feedback, we have open loop configuration, and that is why the magnitude response in the open loop configuration is infinite. However, of course, this is not what we want, so we are going to come up with a solution to that shortly. However, another important thing here is, so if there is DC, any DC component present in input signal, it will produce infinitely large output, theoretically, right? So this is what we discussed, that at omega equals to 0, the V naught over Vi, the magnitude response becomes infinitely large. So if there will be any DC components that are present in our input signal, we saw that our we can take a Fourier series or Fourier transform of the input signals, and there could be a bunch of these frequencies that can present. So if there will be any DC components that are also present in the input signal, those DC components will be amplified infinitely large. However, we also saw that this is really practically not possible, that our amplifier can just give us infinitely large gains, because of that extra power is coming from the power supplies, and we have these saturation voltage levels. So what usually happens is, if we are going to use a Miller integrator circuit in the same configuration, those DC components does not amplified infinitely large, but usually get saturated. So realistically, the output gets saturated at a voltage close to power supply voltage, right? When omega equals to 0. So this is what we discussed. When omega equals to 0, magnitude response infinitely large, our output will not become infinitely large because it will be saturated, get saturated. However, we still don't want saturation, right? So how we can take care of this? We can use another very kind of a simple and intelligent solution, and the way to do it is to solve this DC problem. Another resistance RF feedback resistor is connected in parallel to a capacitor. So what we have now is, we have this circuit, and this was the resistance, this is the input resistance, and this is a capacitor. So rather than just using a capacitor, if we connect another feedback resistor RF here, that will help us solve this problem. Because what will happen is, now that when at omega equals to 0, our XC becomes infinite, capacitor becomes open circuit, right? When the capacitor will become open circuit, we are still going to have this feedback resistor in the feedback loop. So we are not going to get the open loop configuration, and we will not get the infinitely large gain or the saturation effect. So at omega equals to 0, our V naught over Vi becomes our regular gain minus RF over R, rather infinite. So this is the important consideration over here, that we can use this RF resistor to eliminate this DC problem. So the magnitude response, we can also find out the magnitude response of this circuit. So V naught over S over Vi over S equals to minus RF over R over 1 plus SCRF. You can easily calculate this magnitude response. You can easily calculate this transfer function for the circuit as well, with the RF as in the feedback loop. So one important consideration when you are going to use RF, note, is smaller the value of RF, less ideal circuit will become, because feedback will be dominated by the resistor. All right. So in terms of selection of the feedback circuit, feedback resistor, that we need to consider that since this is appearing in parallel to the capacitor, so if we are going to have more smaller values of this feedback resistor, that will that is going to make the circuit less ideal for integration, because our feedback loop will be dominated by the resistor rather than the capacitor. Okay, so this was the end of the lecture today. And in the next lecture, we are going to see one more application before we will move to the non-inverting configuration, the other configuration of the op-amps that we want to discuss in this chapter. So we have one more application. We are going to see how we can differentiate the signal. We saw how we can do the integration. In the next lecture, we will see how we can do the differentiation. And we will also do one more example problem of related to the integrator circuit. All right, so with that, thank you so much. I will talk to you in the next lecture. Thank you. Bye-bye.